Okay, thanks everyone. My name is Aditya Akella. I'm a professor of computer science here at UT Austin, and with me is Chris Rossback, and we're going to be talking to you all about LDOS. So let me start by describing what LDOS is. Um, it's a newly launched center. It's a what is called Expedition in Computing. This is NSF's flagship program for computing, launched last year. It's a multi-university, multidiscipline PI team spanning 5 universities, with the majority of us in Texas. Um, as you'll see, this is work that we are doing in close collaboration with a lot of our industry partners, from A to V, and potentially happy to sign on other collaborating companies as well. And so let me start by describing what our overall goal is. So, all of us know maybe what an operating system is. It's iOS, Android, what have you. What we are trying to do is to build the next generation intelligent and self-adaptive operating system. So just to level set, operating systems are basically at the heart of all computing infrastructure. In particular, what they do is they power our smartphones, cloud, and edge computing, and even emerging tech like personal robots. And essentially what an operating system does is it enables multiple applications that are running on your computer system run together by managing resources that are available, such as CPU, memory, GPUs, and so on. So what's changing in the systems landscape is that modern applications and the environments in which they operate are basically placing a lot of emphasis and sort of like interesting challenges towards resource management. So first of all, if you look at modern applications, they require a large number of diverse resources, variety of accelerators, CPU, variable amounts of memory, and they also have strict performance needs, such as real-time, high throughput, and so on. For example, if you're talking about robot navigation or the autonomous car that we talked about, we need high throughput, for example, for perception tasks. And the systems on which these applications operate are also expected to perform well in complex and dynamic environments. For example, if you have a robot that may be navigating amidst a large group of people, such as the robot we saw at our reception yesterday. So in the context of these modern computer systems, environments, and applications, effective resource management essentially becomes important in order to make sure that these applications run smoothly in these settings. All of this is fine, but then why do we want to redesign the operating system? Is it not doing a good job of resource management? Well, our claim is that resource management in operating systems today is fundamentally broken. And in fact, operating systems today cannot run demanding concurrent applications well, even when the computer system underneath has enough resources for them. So let's take the example of consumer autonomous robots. I think this is also something that we saw in a couple of talks earlier. The underlying operating system may be able to handle the core navigation application just fine. In this case, this is the Jackal robot from Texas Robotics that's able to navigate from point A to point B just fine. But the moment we add a third-party application, in this case, a simple web application, the core functionality on the robot suffers. The robot stumbles, hits various roadblocks, and so on. And this is despite the case that the robot had enough compute resources to be able to run navigation as well as these concurrent other applications. So there's something broken about how the robot's operating system is actually allocating these resources to the running applications. So this kind of, and we'll get into some of the reasons for this, but this kind of poor resource management is something that we think is a key impediment for a variety of important technologies. For example, in the case of robots, it places a fundamental impediment to be able to run interesting added functionality applications aside, in addition to the core functions of the robot. In the case of cloud, today we are unable to run multiple workloads concurrently, pack a lot of workloads together without having them destructively interfere with each other. And in the case of things like edge computing, we cannot run a large number of real-time applications concurrently on these platforms. So the question you might ask is, so what is it? Why is resource management broken? If you think about operating systems, or in fact any systems infrastructure that's out there today, resource management is handled by what are called policies. These are things like your scheduling algorithms, various kinds of queuing disciplines, and so on. And these policies run in various subsystems of the underlying system. What we argue is that the architecture of these policies that run inside these systems is actually broken, and it is this brokenness that leads to the kinds of failures we see in dynamic environments. So there are two aspects to this brokenness. The first is what we call lack of adaptation. If you think about how policies are written inside systems, these are resource management policies. These are all written by humans. They make a lot of static assumptions about the environments where the system is going to operate in. They often operate on limited inputs. And all the aggregate of this means that these manually designed policies tend to make poor decisions, especially when the system is operating in a complex environment. For example, a robot moving in a complex indoor setting. The second issue is one of poor coordination. Typically when you build a large system, people build different pieces of it in isolation. They also design policies for these different pieces in isolation. And as a result, these isolated pieces make decisions that are locally aimed, and they don't end up coordinating, leading to inefficiencies end to end. So for example, in the case of a robot, the robot CPU may schedule the navigation task, but the memory subsystem may not have loaded the map, causing the robot to stall. And if this keeps happening, the robot may essentially not be able to navigate successfully. Now, there are workarounds to this. For example, you might actually throw a lot of resources so that managing resources doesn't become a problem, or you might design custom kernels and custom operating systems for each of these individual environments. But this is expensive, wasteful, and all of these customizations actually immediately become obsolete the moment new applications emerge on the horizon. So this is why we think it's time to redesign and rethink the operating system, essentially bringing intrinsic and intelligent policy decisions into the system to enable optimization of application performance under dynamic situations. And what we believe is that if we are able to make principled use of machine learning, then that machine learning can be a game changer. It can enable an intelligent operating system that can make data-informed resource management decisions end-to-end, meeting strict needs of applications and system-wide requirements in a given setting. And this will help us avoid the need for excessively over-provisioning the system. Furthermore, what we also believe is that such a learning-driven operating system can be self-adaptive, meaning that it can automatically adjust to different settings by retraining. For example, for working for a robot functioning indoors to a robot that may be functioning outdoors, or even a cloud server or an edge server, without requiring any manual customization. So this is actually what we are doing in our expedition. We are building this operating system. But in order to build this operating system, we actually need to realize an operating system design where adaptable and end-to-end machine learning-driven policies are a first-class primary design concern. And our project is essentially designing these kinds of operating systems, which we broadly call learning-directed operating systems, or LDOS. And as I'm going to show, our research plan has sort of cross-cutting ideas that span core systems design, generative AI, and machine learning, and formal methods. But let me actually tell you why it is we need a clean slate reboot of the operating systems design. The reason is this. So this is actually kind of an overly simplified version of what the Linux stack looks like. And if you see, it's extremely complex. And the locations where Linux makes decisions on how to allocate resources are spread across the entire stack, shown in those blue circles. And the data that the policy needs to make these decisions are also spread across all through the stacks, shown in these red circles. So given this complexity, how do you actually systematically introduce machine learning, data-driven decision-making into Linux? And this is kind of why we feel that this structure is not something we can operate with. We need to rethink what this looks like. So what we're going to do in our project is essentially look at a new class of machine learned algorithms that are trained on rich runtime data, some of which is synthetically generated, and ensuring in particular that these policies, machine learned policies, are provably composable end-to-end, and they're formally verified to guarantee application and system requirements are met. On the operating system design front, we are developing new building blocks that enable low overhead decision-making driven by machine learning inside the kernel, low overhead inference, and also automatic model updates. Importantly, and reflecting on the talk that Mike gave a little earlier, we're also building this notion of guardrails that enable safe auto-adaptation of the operating system when learned decisions are being used inside the system. Okay, So what I'm going to do is basically go over a couple of these works that we have done so far in our group. One other thing I want to mention is that we don't want to just build these research prototypes in isolation. We are also keenly interested in realizing some of the benefits of our new operating system in exciting use cases. In particular, we are targeting 3 classes of use cases. One, enabling robots to become sort of like the smartphones of the next generation, where you should be able to download apps from a robot app store and run them on your robot alongside the core functions such as navigation and perception. Also, enabling clouds to run at much higher utilization and offer performance to core running tenants, and enable heavy multiplexing of edge environments. And here's a list of companies that are already participating with us and collaborating on helping us realize these use cases in the context of LDOS. And a bunch of other companies on the bottom that are looking beyond these use cases, specifically Meta and Nutanix, for instance, looking at AI infrastructure and at the other end of the spectrum, Bosch and Toyota looking at vehicular computing. All right, so one of these use cases is also something that we'll be briefly able to touch on during this talk. Okay. So what I'll do now is switch gears, get a little more technical, describe what we have done so far on this front, starting with this idea of property-directed learning, which is a key building block of the use of machine learning inside systems in our project. So the motivation for this problem comes from the fact that if you ask any system builder and say, why don't you use machine learning inside your system? The most common concern they get is one of skepticism. And what happens if learning does something wrong and it doesn't really meet what I want it to do, but instead does something else that can lead to bad side effects? In fact, this fear is not totally unfounded. Here's an example of something called a congestion controller. This runs inside all of your operating systems, controlling how fast data is sent or received by your computer. And this is a learned congestion controller shown here in this dashed line called Orca. What's shown on the left-hand side is if you take this learned congestion controller and you add a small amount of noise to the input that goes into this learned congestion controller, perturb its features, its performance really tanks. It should be hugging the blue line on the top, but its performance really tanks. So it's highly non-robust. The second thing also is that what we see on the right-hand side is that the congestion controller often gets into doom loops where it makes a bad decision, and because it relies on a feedback loop, it continues to make worse and worse decisions, resulting in extremely poor performance. So what we want congestion controllers to be able to do is be able to adapt to various environments and offer good performance, but also avoid these bad side effects. Ideally, what we want is a learn policy pi here to be able to satisfy some desired property of interest phi here with a proof c that the property can be met by this controller. So for example, you might have a property in the context of congestion control that says if network is extremely good, then I should be able to send at a high rate. Or if the network has started to not look so good, then I should be able to reduce my sending rate and match the network's available capacity, right? So the question is, how do you coax the learned congestion controller to always meet these desired properties that a designer of congestion control may want? One way that can be done, that this can be realized, is by introducing these notions of certificates. So a certificate is a formal proof. So for example, you can use something called abstract interpretation. And what this does is it analyzes, in a worst case sense, the entire input that is available to a learner. And it asks the question, when I morph this input to an output, is there any output point that violates a property of interest for me? And it provides a certificate proving yes or no. Now, one can use these certificates to understand whether a learned policy meets these kinds of properties, but the problem with these certificates is that they are binary. They give you a yes or no signal, which is really not very informative for training or guiding the learner towards a good policy that eventually also meets these properties. So what we designed is a new mechanism for learning called certified learning, which essentially introduces the notion of a quantitative certificate. Instead of giving you binary feedback, it gives the learner quantitative information about the fraction of input space that can be provably shown to meet a given property at any given point of time in the training. So the idea is that in each training iteration, you get this quantitative feedback that you can integrate together with your loss function and differentiate over the two of them, such that when your training converges, your learner not only satisfies the loss function, but also provably satisfies the property of interest. So here's a link to our paper. These are a few results that show that we actually match the performance and outperform several of the existing state-of-the-art mechanisms. For example, BBR here is a state-of-the-art Google congestion control that's deployed in, for example, a Chrome browser, and we outperform that. And we also have provable certificates that this learned congestion controller actually adheres to the properties of interest for you, the designer. Okay. So at this point, I'm going to switch gears. I'm going to invite my colleague, Chris, to talk about ConfigBot, which is, as Chris will talk about, config tuning for robot operating systems.
Thanks. We've been practicing that handoff for weeks. I think we finally got it down. Okay. So in the next couple of slides, I'm going to be talking to you about ConfigBot, which is a system that we've been building and developing to tailor resource allocations in robots based on the workload and environment that the robots are in. So to put this in context, let's revisit some of the videos that Aditya showed you earlier in the talk. Oops, went the wrong way. There we go. Let's go the right way. Okay, so robot deployments today, such as the robot you're watching here, are often over-provisioned and restricted to run only a static set of applications at runtime. And this is done to ensure that resources are always sufficient, right? And this is easy to see in this particular video where the robot navigates very smoothly through the environment. However, as Aditya also showed you earlier, when we try to add a second application to this setup, we immediately see problems with the robot stumbling, struggling to walk. And now you might argue that, well, you shouldn't do this, right? You shouldn't oversubscribe the hardware by adding the second application. But in fact, what I'm going to show you in the next few slides is that you can safely co-locate third-party applications like this one without oversubscription and without having to compromise on the performance of core functionality. So at the core of this, of course, is the obvious idea of preventing degradation by setting limits on how much resource the second application uses. But as I'm going to argue in the next slide, finding optimal resource limits is actually a pretty challenging problem. And there are really three main facets of this challenge. First, robot applications are complicated, right? What you might think of as one logical task or application, such as navigation shown here, is in reality a collection of loosely coupled processes coordinating with each other, which yields a fairly complex set of dependencies. Second, each of these tasks operates at potentially very different timescales, right? That can range from tens of milliseconds to whole seconds, with each task having potentially different priorities. And finally, even if the robot is running the same set of applications, resource usage can vary pretty widely depending on the environment. For example, we studied a number of navigation apps and found that the number of CPU cycles consumed by the navigation loop could vary as much as 3x, depending on whether the robot is in a crowded environment or an empty room. And consequently, if you provision for this worst case, you're basically guaranteed to underutilize resources pretty dramatically. Okay, and this is the problem we're going to try to fix with ConfigBot. Now, if you look at the state of the art, the most obvious way to try to improve the situation is to go ahead and set some limits on this second, additional application, right? And the standard way of doing this today is to use control groups in the operating system, or C groups. Okay. Now, this technique will let you set limits on things like how much CPU is used, how much memory, I/O, or networking, and it basically puts an upper bound on what a process can use. Now, we've found that while C groups provide good control over resource usage, they're actually kind of insufficient in our setting. In particular, they're insufficient to allow us to maximize utilization. So our system introduces a second way to modulate usage through a novel abstraction that we call an adapter. Adapters can ultimately be thought of as configurable fine-grain flow control. Most robot applications today function by communicating through their data dependencies. For example, an object detection application computes only in response to a new image frame, right? So if you use an adapter to modulate the flow of those images, you can essentially control how much downstream compute resources are used in the rest of the data flow graph. And this is what adapters allow us to do. Now, this slide is showing you an overview of ConfigBot. And the left half of the slide shows the learning process. ConfigBot learns new configurations that fit the current environment through multiple steps of a Gaussian process that meet a developer-defined specification. And this specification includes both performance constraints and performance objectives. The right half of the diagram shows what happens after a new configuration is deployed. ConfigBot maintains a library of configurations and monitors the system to detect when to change between them, or potentially return to the learning step to handle a previously unseen environment. So to give you a little taste of some empirical results, the first slide in this section of the talk showed how poorly the pathological performance of a robot when we added this third-party application, and this was due to poor default OS resource management. And what you see here is now ConfigBot using exactly the same amount of resource and navigating quite smoothly. But wait, it doesn't stop there, right? Indeed, the default operating system with even 4 times the number of CPUs actually fails to deliver the same navigation performance that ConfigBot is able to deliver with a single CPU. So we're pretty happy with that result. And of course, there's a QR code up here for people who are interested. Please take a snapshot and see the paper for more detailed results. And at this point, I'm going to let everyone who's obviously taking pictures continue until they are done, and then take a soft left turn into the next subject, which is another system that we've been working on for quite a while now called Kermit, which we think of as providing an MLOps-like development environment for our learned kernel policies. And this system is really addressing one key pain point, and it's our pain point, although it will, we project, become everyone's pain point. And that pain point is that putting ML in the operating system takes a very long time. And to understand why, you can think about it in terms of this canonical situation that we encounter over and over again. Some researcher or grad student, call them X, decides, I'm going to investigate the use of ML in the operating system subsystem called Y. Now, X is going to run into a number of issues right off the bat. And the most common one is that it's very rare to find researchers who are both great OS hackers and great data scientists and ML developers, right? And typically, people crash out pretty early on due to lack of good skills in one or the other. Another problem is that in general, we don't know going in if subsystem Y is actually amenable to the use of ML, right? This turns in turn into a data collection problem and a sort of a model selection, technique selection problem. And moreover, if researcher X, uses some technique in Y and it doesn't work, how do they know that this says anything more than I chose the wrong technique? So we need the ability to iterate quickly. And then finally, how does X develop and train the model and then deploy it in the OS when the tool chain for developing and training models is really not currently OS amenable? So really the root cause of this slow progress that we saw early on was that the OS developer workflow does not look anything like an MLOps workflow. So solution? Let's unify them. So what the system Kermit does is essentially provide this MLOps-like environment for developing kernel policies. We really want people to be able to come in and essentially use PyTorch directly, collect data from the kernel without caring whether it's coming from the kernel or maybe even knowing whether it's coming from the kernel, train and validate a model, and then press a big button that puts the model magically into the kernel. And that's what Kermit does. It has 3 components. It's got a k-collect component, which operates in user space. And you can think of it as putting a data frames-like interface on top of data that is actually sourced from the kernel. And it does this very transparently, allows developers to use tools that they're familiar with directly, like pandas and PyTorch, without knowing that the data is coming from the kernel. We add a feature store, which for those who are familiar with Lake, which is probably not many, but is our previous work on putting ML in the operating system. It's an in-kernel feature store that both exposes data that is sourced from the kernel, but also provides a coordination point for invocation of policy decisions directly in the kernel. And then finally, there's a K-deploy. Note the clever use of the letter K, which helps us do this push button kind of deployment where you train and validate a model in PyTorch using Python. Newsflash, the kernel does not run Python, but what K-deploy does is cross-compile it to C, build a kernel module, and automatically deploy it for you. So this, we found, has really drastically reduced our cycle time and has allowed us to involve people with a much broader range of skill sets and people who are very curious but need to learn. So with that, I'll sort of close by pointing out a handful of resources that we want you to take note of for LDOS. We're very committed to the open source ecosystem. So we have a public GitHub, which has both the LDOS kernel as well as trace generators, models, and a bunch of educational material. Please go take a look. Feel free to get involved, contribute, use. There are events that we hope many people here will be interested to participate in. Every year we have an industry day. It's typically in the fall. Last one was in November, so my guess is the next one will also be in November. So please plan to attend that. And if you want a more frequent cadence of interaction with us, we're going to be starting in summer a monthly Austin area SysML meetup where people who are like-minded about this kind of problem can get together and have fun discussing. We're also very committed to the educational charter of our NSF expedition, which means more than just educating grad students and undergrads. We are getting involved with students of all ages, creating things like summer boot camps, reading groups, research projects, and then PhD summer research school as well. So thanks very much for your attention, and maybe we have time for questions, maybe we don't. I don't know, do we?
Question. So just to make sure I understood correctly, so part of the direction in this area was just kind of like solving those gaps in system resource utilization, and then the other half was kind of solving problems from OS level potential crashes and issues, and having more flexibility in handling those in weird situations. Is that kind of like a decent summary?
Yeah, I think that's a reasonable way to understand it. I think those two things are actually kind of fundamentally related, right? I and hopefully my collaborators will look at this problem as really one of trying to maximize utilization, which in turn drives down sort of consumption, has nice properties for the environment. But why can't we do this with existing techniques? It's because the ecosystem is evolving so quickly. Applications are changing, and the hardware is changing faster than a handful of OS developers can possibly keep up. And operating systems need to run in so many diverse settings that our vision is to be able to very quickly adapt. And then the benefit of adapting is precisely what you said. We can actually minimize the amount of resource required to accomplish the objectives that we want.
So kind of a follow-up to what's been asked before. So if this is on ML, and what if it's an unseen condition that happens, and how it's going to perform? Especially, I see the robot performs well this time, right? But what if Wi-Fi and more connections are added and not considering training?
Yeah, absolutely. Do you want to?
Yeah, sure. I can speak up. So one of the things we did not get a chance to talk about is this notion of guardrails, which we use as a framework for online monitoring of the quality of decisions being made by machine learned models. And we use guardrails also to trigger actions when violations happen. So in the case of the robot, for instance, violations would be constraints for core services that are violated. For example, not being able to service a core application every so often, in which case we go back and relearn a new policy that works for the newly encountered environment.
I had a question on the system safety. You mentioned the config bot enables increased performance while preserving system safety. Could you elaborate a bit more how it does that? I'm thinking especially in vehicle applications.
Yeah, sure. So I think the key insight here is that some applications are core or critical and some are not, right? And the idea here is to ultimately optimize for two things. We want to choose a configuration that satisfies some set of constraints. For example, the key things that keep the vehicle on the road execute frequently enough that the vehicle stays on the road. And then the objective is then whatever remaining slack in the system is available can be allocated and actually utilized by something that is less critical. Does that make sense? Yeah.
Okay, let's thank the speakers once more.